Start with like what we like to talk about today. So I will talk about object recognition, and I am getting quite a bit confused, honestly, because I have these two courses, as you especially Joe know about that there's a little bit overlapping. So sometimes I'm not sure I talked about this before or like not, and then I need to check back. And I'm not even sure I showed this. Maybe you saw this before, but maybe you did not. So how many circles did you see here? No? None? How about now? Still none? Do you see some? Yeah, you see some now? Not quite, actually quite a lot. Actually, you see more than... actually... okay, you see this probably? I'm not sure if this kind of maybe it's more like ellipse. But, I mean, okay, that's why I don't know. Always like it's not so clear about like recognition, like what you see and what. So another like key example is like how human interpret stuff. So I guess both of these are valid, but somehow we'll say like the second one just doesn't seem right. Actually, the first one doesn't seem right also. There's another kind of, I don't know, kind of cute reference, I would say. But I don't think we have like this crowdsourced steering yet. I'm not sure. Yeah, but honestly, when you watch the news again, like 747 Max. Oh yeah, I don't know, but it will eventually happen, right? You know it will happen because what I mean is when you replace this actual like mechanical design using some kind of software, and you know the software eventually will have bugs, and I don't know why people like just think that like they can just adjust design. You read the news, right? Kind of like. They basically, according to my understanding, is that they try to save gas. So they have like it's more efficient in terms of gas, in terms of the design, but also you can increase the capacity. But somehow with this kind of like mechanical design, you need to make the nose of the airplane to tilt more upward. So sometimes it will tilt too upward. So then they try to have a software just to adjust it somehow that like if you think it's like too upward, then you just tilt it down, and then I don't know what they're thinking. Apparently, you will have bugs somewhere, and then you will kill people, and yeah. So anyway, I don't know how it will end. So I'm not sure. Like, of course, like recognition is about just okay. When we talk about recognition. Yeah, you read that news, right? Yeah. So I don't know how it ends. Like probably like it's not going to end so well. Yeah, no idea. So, but anyway, so we will talk about this recognition in a pretty general way. So, and of course, it's kind of like a part of this machine learning stuff. I guess I showed these slides before. I'm not sure I showed these slides before. But if you think of like machine learning, there's like basically several different main problems you can classify into. Group into 7 main problems. Like if it depends on like the setting, like whether you have the supervised problem or unsupervised problem, whether it's discrete or continuous. I mean, if it's discrete and supervised, it's a classification. If continuous, is regression, and so on. And so I guess I would just jump through this. I mean, but anyway, okay. But basically, if you think of like all these classification problem, or like when you have a picture, you're trying to recognize something, you're really just trying to model or like try to like tune a function. Basically, you can think of like what you're doing is nothing but trying to tune a function such that this function will output your desired output, right? So and then basically I have some input, like it can be X here, and it can be the original image, but I guess for the last decade it changed a lot, but before the last decade, most of the time you start with, let's say you have this image here, and you try to extract some features. And from these features, you use some kind of classifier. It can be like last generation would be like, say, support vector machine and so on. And you have this training label there, and then you train the classifier. So basically, you just have compare with this output here, compare the ground truth of your output, see if it's good or bad. If not, just address this classifier. So so this is all pretty standard, and the classifier you can think of like it's just in higher dimension. For example, in 2 dimensions, it's basically just trying to separate your data full, okay, in very kind of what should I say? The most basic way would be just trying to kind of separate your data with some kind of hyperplane, right? So you're just looking to trying to find like to model this hyperplane basically. And of course, in terms of testing, you're basically repeating the same thing. You extract the features and go through the classifier and have the prediction. And this is an example, like trying to do scene categorization to see like, okay, which is the kitchen, for example. And in terms of machine learning, there's always a buzzword about like bias and variance trade-off. So, and basically when you're saying the model is biased, it's basically it's really the model is too rigid, that is not enough flexibility, you cannot train it. So for example, like in this case, you're trying to fit kind of a curve on this set of data here. So if the model is like too rigid, as you can see, like it just basically cannot really fit the data, right? So that would be like something is the model is too biased. So if the model when you say it's like too much variance, then basically the model is too flexible, then probably it's not, in this case, not extreme enough. I would say if really extreme example would be like basically going through all this testing data, I mean training data. But anyway, so okay, let's get to the computer vision part. So when we're saying that we're trying to recognize something, so of course we want to say like recognize to what. So we need to first say how many potential categories there are. Like what do you think? Like how many potential categories? Someone did some research there, like back in 80s, like Biederman. I don't know whether I pronounce it. Is that Biederman or Biederman? So he estimated like 10,000 to like about like 30,000 of those different categories, and of course you can go pretty like usually like these categories are actually structured, right? So you can form a tree of that, like animals, vertebrae, and go down and so on. And for computer vision, actually, you can think of like categories will be in different level also. Right? You categorize stuff like in terms of, for example, just the scene, very high level, like as a whole, like what is the scene is about, and you can go down into a lower level that like okay, what objects are there like in the scene, and you can be more specific. For example, I just only interested in pedestrian or like cars and so on, and trying to detect all these objects. And we can also like have semantic segmentation. So semantic segmentation means that like I'm trying to find for each of the pixels in the image like what is the oops, I guess I'm sorry about that. Let's see is that okay, just showing the okay. Yeah, it's okay now. So what just I said is like if for semantic segmentation, it would be like I'm trying to for each of the pixel there, I'm trying to say like whether this pixel belongs to a mountain, like on the a pixel in the sky, and so on and so forth. So doing recognition is all about modeling variability. So these variabilities including like camera position, illumination, and also like the shape, like how the objects you are detecting with different shapes, then it just looks different. And there's also within class variations. For example, like even though we say that something is a chair, they can be very much different, right? Different types of chair, they're all different. And think of like there's all actually if you think of the space of all the images just as an image of 100 by 100, it's really you have what or like 1,000 by 1,000 would be like 1 million dimensions of space, right? So it's actually a huge dimensional space, and within that, like most of the combinations of these pixels values are not natural images, right? So if you think of like in this high dimensional space, it's only a small kind of fraction of this space is actually correspond to like lateral images, and out of that, like you're trying to look for okay in this space here, so this image like form then is correspond to something that is interesting I can extract from there, and so on and so forth. Let's look at a little bit of history. It's kind of interesting. You see, like it's actually just think of that. Like this whole area started like in maybe like 50s, 60s, right? Actually, before even showing this, like what do you think like people started with? Like what is the approach? For example, you have this image here. I trying to recognize something. What's the first thing you think of? Like I trying to how do you approach this problem? And sometimes it's hard to separate like image understanding and recognition, right? Let's say I say I'm trying to understand understand that there's some person in a person may be more difficult, but maybe you have a car or something, then when you're trying to recognize the car, maybe you also try to understand like, the orientation of that car. And these kind of problems actually hook together. But okay, get back to the problem, the questions I asked earlier. So what do you think? Like if I try to tackle the problem to begin with, I guess some of you guys actually propose a project doing that exactly. okay, if I guess like the first thing, at least for me, I'm not if it's biased, but I remember that like I did an undergrad project trying to track a ball or something. The first thing I try to do is just campaign matching. Okay, but at that time, even that is too much. So what I try is I just try to match color. Of course, the result is not good. But what I mean, it seems like campaign matching is like the first things to go. Like right? It looks like if I have trying to recognize something, then for example, I'm trying to recognize a face. It looks like the first thing I try to do, maybe like I have a lot of like face images. Maybe I'm trying to just match them and see like if it works or not. It seems to me like this would be like the first thing I would try. But surprisingly, I think like the earlier approach is quite a bit ahead of the time. Like or not, I'm not sure. But the first thing they think of is all geometric approach. So they really think of like the kind of like what I want to say to start with. They look at these complicated 3D models to start with, but of course like they also simplify a little bit. For example, like the first couple work, maybe probably even the first work, maybe like by like L.G. Roberts, like in MIT, he just start with like something. He kind of like of course, I simplify the problem quite a bit. He only think of a block world, so everything is very simple. Like this block is just made of this block. I'm trying to recognize that. So because it's just block, then he can just build the 3D models out of that. He have all this edge detection, detect the edges, and just think of all this geometric behavior when one object is in front of the other, like how the line is going to be occluded and so on. Actually, in that era, like from we can say like from 60 even all the way until 90s, there's quite a lot of work. It's all based on like 3D geometric approach. So, for example, like of course, like in this case, like for example, like this have works like listed here. When you have like more complicated objects, become more complicated. And for example, airplane, they still try to do that, but you just split into like smaller pieces, right? But kind of like regular pieces. And then like people try to have like more complicated like shapes, like have like using like this kind of cylinders and for example, like Biederman himself like have all these primitives. He call it like geons, and then he just think of like all these objects is kind of combined using these geons, and the problem is that this complexity will goes up pretty quickly. So, for example, like when you think of an object, trying to visualize that, like you can build a kind of like objects like just like how do we call that? A polyhedron, like it's kind of like have multiple faces. When you look at it from different views, and you will observe different shape there, right? For example, this is an example just from different views there, like it just looks very different. And they try to build this so-called like aspect graph to describe that. But the problem is that the number of views just increase really, not exponentially, but very quickly with the number of faces, like in the order of like n to the 9, something like that. But I don't know. What I'm saying, like, okay, this kind of old approach, maybe like 2 decades later, people will just come back to that because now they think that, okay, computational-wise, it's affordable and we can use it now. An example is not here, but an example, for example, in communications, if you know, like people do this error correcting code, in the last generation, like 4G, for example, like they have so-called LDPC code, low density parity track code. And the original paper is introduced in the 60s, and also by an MIT professor, and when he was a student there. And people rediscovered this kind of code in the 90s, and then they find that it's already invented in the 60s, but at the beginning they didn't realize that. So therefore, this likely, I guess, maybe we will repeat this cycle again. So and then in the 90s, they go for this appearance-based model. That's more or less like what I talked about at the beginning. So they just look at what it looks like. So for example, now they have these faces. They just kind of we can think of this template matching again, but okay, of course, Eigenface here is for face recognition. I will go into that in more detail, but in a layman level, you can also think of it's really trying to do template matching in a sense, but in a very careful way. So, but one of these limitations, though, for this kind of when you try to recognize, of course, for Eigenface, you are trying to not just trying to detect a face, but also trying to recognize a face there. So the problem of this kind of approach is after you match, first thing you need to do is you really need to locate that face very precisely. So it's not sufficient to start with an image and try to recognize right away. So you need to have a very good registration, and that means that you just defer the problem. You still need to first try to detach them before you can recognize easily. So there's some other approaches that I'll just skip through that. Okay, this is actually interesting. That people try at the beginning is to think of the shape model, how it looks like in the kind of image space. So of course, the original image space will be really large, right? So if you think of, as I mentioned, 1,000 by 1,000 pixel will be a million. Kind of the dimension will be a million. So, but you can kind of do a dimension reduction, just reduce the base, for example, using PCA. So there's some work people did in the 90s. For example, just for this kind of toy duck here, you just want to see if you just look at it in different poses and how it changed in the image space. And you can see this kind of interesting, I don't know, curve here in this high dimensional space, how this pose changes. How the image changes according to the pose. And then in the mid-90s, actually, it's kind of interesting if you think of in terms of math of capacity of the requirement of understanding. It seems to be getting easier and easier, right? In the 60s to 90s, you need to understand this geometry a bit. And then in the 90s, people just giving up, and then, okay, let's just think of this appearance. And then in mid-90s, I even go simpler. Okay, let's just do sliding window that everyone can do, even in kindergarten. So you just go through the image all the way until okay, you hit something. And then it's really simple template matching now, right? You just swap through the entire image and then try to match one by one until you hit the target, basically. And this sliding window approach was used for quite a while, and in the sense that it's still kind of used. If you, for example, Joe mentioned YOLO a week ago, I guess. And in the sense at high level, you can still think of that as partially a sliding window approach, even though you do not slide exhaustively, not one pixel at a time, but you slide block by block. And then after mid-90s, there's a change to local feature approach. For example, SIF that we mentioned earlier. Then in the sense now you assume like camera position and illumination changes, but you assume the shape there like doesn't change too drastically. So locally is you can have basically some local feature, what I'm saying, you can extract from that object. So of course, if the object just distorted completely, you cannot get any local feature, meaningful local feature, right? So and this is an example. I guess you guys probably saw this before, like when we talk about shift, right? So for example, if I try to match objects like shoes here, I just look for local feature like key points like from the shoes there, and then trying to in the image look for key points that correspond to shoes, and then trying to align that. It's actually quite successful in terms of large scale image search. So if for example, if you have lots of different photos from scenic sites, and then like trying to recognize where is that site there, and then you just get local feature and trying to index them, and just find correspondence, and yeah. I'm not so sure, like maybe at the beginning, like early version of like, for example, Google Goggle, when they look for landmark, maybe they use SIF or something like feature approach, but most likely now they use deep learning. I'm not sure, yeah, actually it's, but I'm not sure, like earlier, yeah, I think earlier version probably they did use like some of this local feature approach. Then, of course, afterward, before deep learning, there's still like one step. It's like doing this parsing shape a model. That's actually quite natural also, right? When you have this local feature, for example, you have this model here. I can recognize like where's the eyes and nose and mouth. I want to like recognize this as a head only when the eyes is a pair, right? The right eyes should be next to the left eyes and on top of the nose and so on. So we want to kind of like also specify the relative locations of all these parts there. So therefore, we have this parsing shapes model there. So you can use that to recognize different things, like for example, cars. So you expect that like the headlights is here, wheels is here, and so on. And this is a pictorial example to recognize, for example, like pose of a person to find the joints there. So so this is just a probabilistic model. So if you're familiar with probabilistic models, it's actually pretty simple here. So you can have for each of the local joints there, like you can assign a probability for that. Given the image, how likely this is, for example, how likely this joint here is the joint, I don't know, how do you call the joint here? Anyone know the name of here? Elbow? No? Oh yeah, elbow. Yeah, I think it's elbow, yeah. I'm sorry about that. Yeah, this is something I didn't study like kindergarten well. So, yeah, and then like your elbow, shoulders, and so on, you recognize all this joint there, right? So, okay, locally, you say like there's some probability, this is elbow there. Then you can say like from elbow to shoulder, like what do you expect, how far is that, right? And you can assign a probability of that, right? If like your elbow, you detect elbow is like from your shoulder is like 1 meter away, that is quite unlikely it's correct, then your probability here is pretty small, right? So, but if it's like, I don't know what it's supposing saying it to be, like 20 meters or 30 meters, 20 centimeters or 30 centimeters, or like a little bit more than a feet or something, then you say it's like the probability is high, right? So then the whole thing, you can just multiply all these probabilities together, then you get a pretty good model out of that, right? So then again, you're just trying to maximize the probability, right? In the sense, you're just trying to change all these PI, these locations here, such that this joint probability will be maximized. So locally, like oftentimes, like to identify this local parts, for example, the elbow or like the hand, like before deep learning, a very popular approach to find that is just using HOG. That we already studied that. So we just change the HOG to recognize, okay, this is hand and this is elbow and so on. And then afterward, there also like a so-called like bag of features model. This actually is just borrowed from like bag of works in language model. And it's interesting, like, because in the sense I think this is an easier model than the part model, right? But I guess somehow maybe this is easier to train, so work well. So it's like kind of fashionable for a while actually. And if you think of the bag of works model, it's really simple. Right? If you look at languages, for example, if I need to classify a piece of documents, so I have like kind of like state of union address in different era. So I don't, if you just don't look at this here, if you just look at like what is the keywords that appear most often, you can kind of like recognize like the era there, right? So this is like Iraq and terrorists, most likely is doing W. Bush, and then like that's, for example, I talk about a lot of Soviet like nuclear weapon. It's like during the Kennedy era, and that's like talk a lot about like Japanese war and so on. This about in the Roosevelt that time, like Second World War, and the idea is like basically, okay, of course, a problem is that in images and videos, we don't have lateral words, right? So then we need to figure out like what is this tiny component there. So basically what we are going to do is just train it. In the sense that if we have a texture, so to classify different texture, for example here, for example, like for this texture, you expect that you will see more of these words here or these features here, and for this texture, I will see more like this kind of like features here. And we can get these words like full training, as just I mentioned. So after training, of course, you can just do a histogram for classification, right? If I have this basic dictionary that I have decided, so to classify this several different textures here, as you can see, like if I build a histogram of that, just sample over all these bed of words here. So for example, like for this pattern, I will have like a histogram like this, right? Most of the time it's like showing these several features here, and for these patterns I will have this, and then the last one I have like this here. And so just a little bit repetition of like what I just said. So this will summarize the step during a bed of features training and classification. So we need to first have a feature extraction. So that will be like at least two ways to do this feature extraction. Right? You can do it like regularly, just over the grid, or like you can do an interest region, like for example using key-point detectors as in SIF and other like approaches. And then after the extraction, then you need to compute the after the key point extraction, you need to extract the features, right? So that's basically extract the descriptor. So yeah, again we talk a lot about that like in SIF. So have the descriptor there. Then now we need to build a dictionary. So in that case, we'll be just using a simple clustering approach, right? So you have a bunch of data here. So we have all these the features, and then we just cluster like the features together and get some representation. So then this will be our visual vocabulary. So then we build a codebook there, and during testing, we just reverse the step where we not exactly reverse the step. Then we again extract the features. Extract the key points, then extract the features, and then like see like which features the features belongs to which of the vocabulary group, and then just do the histogram, and then use the histogram as the features. So for example, this is a example of building the codebook basically, right? So this all of this wheel is more or less the same category and grouped together. I'm taking average. This has another wheel here. I'm taking average of those. There's some issues, for example, like how to choose the vocabulary size. We don't want to be too small. Too small won't be representative enough. If too large, then that would be like overfitting. Also, like in terms of computational efficiency, we can build hierarchy in terms of for the features. For example, like build a computational, have a tree to kind of okay, let's see actually. Yeah, actually, I'm not sure. This is like doing. I think it's doing detection. So yeah, you can build a tree in the sense how it's going to be efficient. It's like you can group the features to the neighborhood. Right? For example, like if I have these 2-layer trees here, and I have this is the features extract here. So instead of comparing each of these, I have basically like 9 of these different groups here, right? So instead of like trying to compare to all 9 of these, I can just compare with the central first of group this 9 into 3 each. So then I will compare with like this kind of 3 groups, like which is closest. For example, like these guys, this one is actually closer to this group here, right? Then I will first assign to this group first, and then further do the further search. So in that sense, like instead of like I have 9 times comparisons, I need 6 times comparisons. So of course, if you're more hierarchy, then you can have further gain in terms of computational efficiency. And apparently, like for better or worse, why I said like it's kind of going backward compared with this shape and part model, because you ignore one thing which is very important, right? You just look at the frequency or the histogram of how your features, kind of the distribution of the features. So in the sense that these 3 images are totally the same if those are these features there. So of course this doesn't look like a valid phase, right? And this is an even more extreme case. For example, this image is essentially have the same histogram of this guy and this guy, right? So you do not distinguish in terms of this kind of method, like back of features method. Does not really distinguish all these 3 cases. So a very simple approach. I shouldn't go further first. What do you suggest? Like, how can I easily solve this?
Segmenting it?
Yes. We can do we can segment that like into like multiple sub images first, right? And then I compute the histogram for each of them, and then continue to split that and compute that again. And we have additional features for that. So for example, I have level 0 is like that, and I have level 1 have that. Then of course I have like more features, but it's kind of okay. But using that, actually you can do pretty well in terms of scene category classification. For example, this is like classifying different scenes, like with categories like office, like building, mountain, forest, and so on, and using like just bed of features like approach, and also like using this pyramid to kind of like speed your features. You can get like, for example, 80% of accuracy. And you can also use that like beyond scene classification. For example, you can do it for like action recognition. So you have video sequence. Now the patch will be 3-dimensional now. So you have this kind of like this patch is actually correspond to walking, for example. This, I'm not sure it makes sense. Okay, it's like hand waving. This probably makes sense. Hand clap. Oh yeah. Anyway, so that's more or less what I would like to talk about today, honestly. Then of course the present trend is deep learning, and I don't know. I may spend a lecture or two like on that, but later on, and or you can take my class like next year if you are not taking it like this year. So I don't want to spend like 4 or 5 lectures on that because that would be too much overlapping with my other class. So maybe 1-2 lecture max.